Let us figure out the loveliness of circuits. Circuits are awesome.
You never gave us the V equals IR equation.
Oh,
I'm just kidding. Just kidding.
I've given you this equation, V equals IR, Ohm's law. I've given you that resistance equals resistivity L over A. I've given you that current equals dq over dt, or that's just the change in Q over the change in time, right? Okay, we got that. What I didn't give you last time, and I'm glad somebody mentioned something, was the power equations. Let's talk about the power equations real quick before we get into circuits. Okay? The power equation is power equals I times V. All right? That is our basic power equation. Now, let me see, because I skipped that last time, and I need to go back and make sure I don't forget anything. Oh, yeah, I know what I want to do. Here, let me show you where that comes from. What's power again? Work over time. Okay, now, what is work?
Change in energy.
Okay, work is FD cosine theta or FR cosine theta, or we can think of it in the bigger sense that work changes the energy of the system, right? So this is the same as the change in energy over time. Okay, what kind of energy are we changing in a circuit? We're changing electric energy. We're turning electric potential energy into something else, right? Like light or sound or heat or something, right? So this is a change in electric potential energy over time. Okay, what's our equation for electric potential energy? We have two. There's the
Q1, Q2 of R.
1/2 CV squared.
There's the K Q1 Q2 over R CV squared. No, that's for capacitors. For capacitors, that was 1/2 QV equals 1/2 CV squared. But that's only for the energy stored in a capacitor. Okay? So we don't want that one. But what's our other one? What's our equation for electric potential energy that involves electric potential? V.
VQ?
Very good. It's VQ. All right? Now if I have delta change, or a change in potential energy, then that's going to be equal to delta VQ, right? Okay? Now I'm going to rearrange this slightly. I'm going to change it to V delta Q over delta T. What's delta Q over delta T? Current. So that's how we get power in an electrical circuit. We just start with our basic definition of power, work over time, and we rearrange the equation until we get to IV. Okay? So we have all kinds of equations for power. We've got power equals work over time. It equals change in energy over time, and any kind of change in energy. So it equals F R cosine theta over time, but remember, what's this R over T, or X over T, or D over T?
Velocity.
That's velocity. So remember, this thing also is force times velocity, right? Now all these are mechanical ways in general. Well, this is the basic definition. This is a mechanical way to find out energy, like mechanical work. Mechanical power. But now we have electrical power, which is I times V. Okay? But wait a minute. V equals IR, right? So if I plug V equals IR in here for V, I get I squared R, right?
Yeah.
So power also equals I squared R. But wait, didn't I tell you that I is equal to V over R? So what if I plug in V over R for I? Then I get V squared over R. So I really have three different equations for figuring out power in an electrical circuit. I have IV, I have I squared R, and V squared over R. I have those three options. Which one do you pick? Yeah, whichever one gives you what you're looking for, right? It doesn't matter. Whichever one is the most appropriate for your problem. If you do not have the current in the problem, then it's probably best to use one of these. Or use this one, right? If you don't have the voltage, then you probably want to use that one. If you don't have the resistance, then you probably want to use that one. Okay? Now, riddle me this. Excuse me. Riddle me this. If I want to have maximum power, really, really big power, then what does the current, what does the voltage, and what does the resistance have to be like in order to have maximum power? So what does this equation tell me? If I want to have big power, I need to have
Great current.
big current and
Big voltage.
big voltage. What does this one tell me?
Definitely big current.
Definitely big current and
Resistance.
big resistance. What does this one tell me?
Big voltage.
Big voltage and,
Little resistance.
uh-oh, that looks good. That looks good. I got problems here. One of them says I need to have big resistance. One of them says I need to have small resistance. Okay. All right. The trick to understanding this, and why it looks like there's a discrepancy, but there's really not. Remember what I said up here, V equals IR? How should we really write that? I equals V over R, because the current depends on the potential difference, really that's delta V, right? And the resistance. The potential difference that pushes the current and the resistance that hinders the current, right? Those two things fight. Now look, what happens if resistance is big? Ooh, current gets small. They're related, aren't they? Okay? What happens if volts get big? Current gets big. Now notice it says if volts are big and or current is big, then power is big, right? So if volts go up, current will go up as well, and power gets big, right? That looks good. But what if resistance goes up, what happens to current?
Goes down.
Okay, so tell me, which one of these is right?
The ones that's going down. That's
Why resistance going down?
because you don't want to decrease current.
Because if resistance goes up,
We decrease.
current's going to go down. And which one's more important?
This I squared current.
Current is more important because it's squared. So I need small resistance, right? The smaller the resistance, the more power I will either generate or the more power I will consume and convert into something else. Okay, so when you go home today, you can, I didn't bring any light bulbs with me. I don't know if Mr. Carter has any sitting around. But if you see a light bulb and you look inside a light bulb, one of those clear light bulbs, you'll see a little filament inside. It's a little bitty wire, okay? Little bitty wire that's pretty long, that's all coiled up, okay? So it's long and has a small cross-sectional area, so it has a high resistance, okay? All right? So what's the difference between a 40-watt bulb and a 100-watt bulb? Okay? Well, power is in units of watts still, right? Same as before. And so if I have a 100-watt bulb and I have a 40-watt bulb, which one consumes more power or converts more electrical power into light?
The 100.
The 100-watt one. Okay, so tell me what its resistance is like. Which one has higher resistance?
The
The
100.
400.
Well, I mean,
Because if you're using more power on the other hand,
If I want more power, I've got to have
a small resistance.
smaller resistance. This one has a higher resistance
Yeah.
than this one. So talk to me about the filament between these two. If they're made of the same material,
name
Which one's longer?
The 41.
This one's either longer or it's
Thinner.
skinnier, right? One of those two. Okay, and you can look at a 40-watt bulb and you can see that the filament is generally skinnier. And the 100-watt bulb, it's fatter. Okay, now think about it for a second. A 100-watt bulb is designed to get the filament so hot that it'll glow. All right? All right, we have those in your house as well. If you have like a range top that's not gas and an oven that's not gas, electric range top and electric oven, they also have a filament. That coil on the range top or that big, thick, honking coil inside the oven, right? Okay, it's a big, fat coil. It's like as fat around as your pinky. And it glows orange. Now, it doesn't glow white hot because you don't want to burn your food, right? But it does. But you do want to generate lots and lots of heat, right? And so that filament has very low resistance. It's big and fat. It's
Pretty long.
pretty long, but it's big and fat, right? So therefore, it has a very low resistance and it generates a ton of heat. Okay? If you want your oven to generate even more heat, then you'd make the filament even fatter still. Okay? So you'd have less resistance and more energy would flow through it for any given amount of time and it would generate more heat. Okay? All right. So there you go. There's power. We have those three equations for power and we use whichever one seems to be appropriate to us. All right? So now that we have that, now we're ready for circuits. Okay? I want you to draw a circuit where you have one battery and you have one resistor and you have one switch and the switch is open.
Got it.
Mine looks just like yours.
Excellent. So it should look like that. Okay, so now it's time to color our circuit. We're going to use our crayons to simulate what the voltage is in the circuit. Now yours doesn't have to look exactly like mine. It just has to have a switch and a resistor and a battery in it somewhere. Okay? Now when this switch is open, okay, first of all, let's do our sign convention. R, O, in fact, I think use this one. Y, G, B, and V. All right, this is low volts. Red is high volts. Okay? All the other ones are in between. Okay? So, if I was going to color my battery, which side of my battery should be red?
Positive side.
The positive side, because it is at high volts. So there's the positive side of my battery, right there. Okay, that means that the other side of my battery should be violet or blue. It doesn't really matter. Just something lower, right? Just something lower. So there's my hot side and my cool side, or the high voltage side and the lower voltage side of my battery. Okay? Now, unless I ground one side of this battery or something, there's no way I know what exactly the voltages are. I just know, or the potentials are, I just know that the difference in between them is whatever this EMF is. Okay? All right, now, remember, when you hook up something that's charged or has a high volt to something else, it shares charge until when?
They are equal.
Until what's equal?
Equilibrium.
What's our equilibrium condition?
Same potential.
They're balanced potential, right? The electric potential is the same. Now remember, our battery has a chemical reaction inside that keeps this side red, high volt. Keeps this side purple, low volt. Always keeps the difference in between them. If it's a 9-volt battery, it keeps that difference 9 volts until the chemical reaction dies or is used up. Okay, so when I touch this wire to this hot side of the battery, that it shares its charge until that whole section is the exact same potential. Okay? And it shares charge over here until this whole side is the same potential. And that's what it looks like until the switch is thrown.
That's not right.
Okay? Because since there's not a completed circuit, charge will flow from here across until this thing is all the same potential, and then it will stop, right? And charge will flow this way until it's all the same potential, and then it'll stop. And then when I close the switch, what happens? Charge is going to flow from high to low, right? So when I close that switch, I'm going to have a momentary time right here when I've got a disconnect right there. I have a difference in potential. And so charge will flow from high to low. So current will flow this way, from high to low. Now the thing is it's going to equalize itself out really quickly. Okay? Some of you may notice in your house sometimes when you turn on certain devices that the lights will dim out and then they'll go back to normal. A lot of times, yeah, hair dryer is a big one, or like when your furnace kicks on sometimes if you have an electric furnace or something like that, air conditioner kicks on, the lights will dim a little bit and then they'll go back up until everything reaches its new equilibrium. Okay? That's what's happening right here. You throw this switch, you got a discontinuity in potential, so charge flows. Okay, now, here's the deal. Charge is going to start flowing this way. So what's going to happen to my purple area here?
Become less purple.
It's going to become less purple. It's going to become blue.
And
And then it's going to become green. And then yellow. And then orange. And then red.
And then, but the battery changes.
Ah, but here's my problem. The battery here is designed to make this side stay purple and this side stay red. So this side over here becomes red. And then I've got this resistor, right? Now, what happens is this resistor, remember, by definition, resists the current, right? And so, will the charge magically flow through the resistor by itself? Okay, will charge kind of magically flow through a conductor?
In a way.
Yes.
Sort of, kind of, right? Because there's very little or no resistance in a conductor, right? Now, we're going to assume that our wires are magical, zero resistance conductors. In reality, it takes a little bit of effort, a little bit of potential difference to cause charge to flow through a wire, but not very much. Okay? What really happens is this part of the wire, this right here, the battery is red. And as I go around here, it takes a slightly different amount of voltage over here for there to be a difference between here and here for charge to flow. But we're going to assume that to be so small, unless they give you some indication that that's occurring, that we're going to ignore it. Okay, we're going to assume our wires have zero resistance unless they give you some indication that they have resistance. Okay? So this wire is going to pick up the same potential as this side of the battery. This wire is going to pick up the same potential as this side of the battery. But this resistor, the current just won't flow through it unless there's a potential difference. And so what happens is this potential difference between red to purple causes the current to flow through this resistor. Does that make sense? All right. All right, so here's my next question. What will it look like if my circuit is like this then, with 1, 2,
Yes.
3 resistors?
Just combine it.
It's gonna change color.
Drop it.
It's all in series.
It's going to be
Well,
red
no,
on
but
the
I mean,
top,
like, it's, yeah, red.
Okay, well,
and
this will be
orange,
red and it'll share its potential with that,
Then
right?
It's going to be either orange or yellow, and then
It's
it's
gonna be
going to go into the second resistor.
Okay, I think all of you got the right idea, is the fact that this can't be red here. Because if it was red,
Nothing happened.
nothing would happen between these two, right? No charge would flow.
We burn ourselves.
It just wouldn't work, right? And it can't, can I go from red to purple right here?
Because then nothing would
No, because then nothing would flow between here and here, right? All right, excellent. So what happens is I've got a color change of some kind. Now, you can pick whatever colors you want. It doesn't really matter. As long as you're going downhill through your Roy G. Biv rainbow. Okay? So it's going to look something like that. All right? Now that's what series looks like. You've heard the term series already before. This is series. In series, you're going to drop a little bit of voltage through one resistor and drop some more voltage through the next resistor and drop some more voltage through the last resistor. Okay? Alright, but there's another way to hook things up, and it looks like this. It's called parallel. And it looks like this. You could have hooked up your resistors like this. Alright, what will that circuit look like if you were to color that circuit with voltage colors?
You know, they say
Green,
Red,
red, red,
purple,
red,
purple,
red.
red, then it'd be like, you know,
It'd be like red,
And then purple.
and then it would be like purple. It'd be so like red and purple, it would be red and purple. Parallel is actually quite boring. It looks kind of exciting when you first draw it, because there's all these different resistors hooked up different. But the thing is as far as voltage goes, it's all the same. You see the voltage here? 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 It's all red to purple. It's all the same. It's all the same every time. Okay? All right. So, one of the things that will help you as you go through circuits is, at the beginning at least, to color your circuits to kind of get a feel for what they look like. Because once we get into combination circuits and with capacitors in there and everything, it gets a little complicated sometimes. And if you just kind of color it to give you a visual feel for what the circuit looks like, it's a piece of cake. All right? So I'm going to teach you a couple of rules. You may have learned these already. They're called Kirchhoff's rules. You know those? Excellent.
most of us.
Kirchhoff's rules, I believe I spelled that right, has two rules.
Two H's?
Is it two H's?
I don't know.
Yeah, that's right. Wait, no.
I don't think there's two H's.
I don't think it's two H's.
I think it is.
I think it's one.
Hang on. I'll tell you.
I have it right here.
It's got it in here somewhere. Kirchhoff.
Really? 'Cause
Kirchhoff's.
Oh, it's
That's right.
yeah, it's two.
it is two H's.
And two F's. Yeah.
We have been corrected.
Okay, these two I'm going to teach you probably different than you've heard before. Kirchhoff's rules are conservation of charge and conservation of energy. That's where they come from. Kirchhoff essentially applied these two ideas to a circuit and came up with two general rules. General rule number one is sometimes called the current rule. You may also have heard it as the junction rule or perhaps the node rule. Okay? The current rule simply says that the current in to a junction equals the current that comes out of a junction. Okay, the current that goes in must be equal to the current that goes out, because otherwise you would be destroying charge somewhere, and that violates a basic law of physics, that charge cannot be created or destroyed. Actually, we'll learn later that you can create charge and destroy charge when we get into modern physics, but it will always, the rework of that law is this, is that you cannot create or destroy a net charge. So if you start with zero charge, you'll end with zero charge.
So you're not destroying these.
Watch me.
Yeah, so what ends up happening is, like, what we'll find out is that you can turn like a photon into two particles, and the two particles, one will be positive and one will be negative, so the net charge is still zero. All right. Charge in equals charge out. Okay, here's our second rule, called the current rule. This is called the voltage rule. Sometimes also referred to as the loop rule. It is that the delta V in any loop must add up to, the sum of any the delta V's in a loop must add up to 0. Okay?
Yes.
Let me show you how these are applied. This is the harder one to understand. Let me start with the hardest one to understand.
I can tell already.
And that's in a parallel group.
This is for any circuit, any loop, okay? And this is for any junction. So this is at a junction, and this is in a loop, a circuit loop.
Where's this for?
Okay? Okay, here's how this works. Alright, you ready? Here's the loop rule. It goes like this, or the voltage rule.
It's like he's gonna
It says, if you start at one spot and work your way around a complete loop in a circuit, any loop you pick.
Has to be independent.
What's that?
Has to be independent.
Well, it just as far as the basic setup of the rule is, you can pick any loop you want. But yes, when you're setting up these to solve, you need to pick independent loops. You can't keep picking the same one. All right. So here you go. As you start your way around, what it says is this, is that there will be devices in here that will supply energy, and there will be devices in here that consume energy. As you go your way around, this one supplies energy or voltage, and this one consumes voltage, and this one consumes voltage, and this one consumes voltage. And when you get back to your starting spot, you need to be back at the exact same electric potential you started at. Or that the addition of volts and the subtraction of volts must always add up to 0. So like for instance, if this was a 9-volt battery, oops, I think I'm dead here. If this was a 9-volt battery right here, so when I go from here to here, am I going up or down in volts? Okay, I just added 9 volts going from here to here, right? Then when I go across this one, let's say this one consumes 3 volts. It takes 3 volts away, right? And let's say as I go through this one, it consumes 2 volts. Then this one's going to have to consume 4 volts. So that I'm back down to plus 9, minus 9. I'm back to a net change of 0. Okay? What happens is this, is if the consumers of the electric potential energy consume less than what's supplied, then there'll be extra volts left over to push more current through, and then it will start to consume more energy. Okay? It's like if I had a light bulb like this, and I hook it up to a big battery, and if the light bulb didn't consume all the energy the first time around, there'd be a little energy left over to shove more current through, and then it would become brighter, right? And then it would reach an equilibrium where it consumes all the energy that's supplied.
Wouldn't it burn out?
And it could burn out. So like for instance, light bulbs are designed for a certain amount of voltage. If you hook it up to more voltage, it will try to push through more than it can handle and burn it up. Some of you may have experienced that when you go to like other countries. I know Europe. I don't know about Canada or Mexico. And I don't know, in Europe, they operate on roughly 250 volts. We operate on roughly 110, 120. So theirs is like double our voltage. So if you take your hair dryer and plug it in Europe, you will fry your hair dryer. If you take a European hair dryer and you plug it in the United States,
It's not gonna work.
it will work, maybe, but it'll work real slow. Good enough for you. It'll dry my hair, but not your hair. All right. If it has enough energy to operate at all, it'll run slow. Okay. So I don't know. Anybody know? I think
So-
Canada's still 110,
So
120. I don't know about Mexico.
Europeans are less efficient than we.
They don't have electricity.
Actually, the higher voltage is a little bit more efficient, but it's also a little more dangerous as well. Actually, some of the
Risky and efficient.
that's correct.
Yes.
Some of
I think I
the
know where we're going now.
devices in your house actually work on 250 volts, like your oven, your range top, and I think like your air conditioner, and it may be dryer. Your dryer unit, if it's electric, it'll have a different type plug, a bigger round plug that you have to shove into the wall. That's 250 or 240 or whatever, 220, whatever they call it. Yeah, and they got different ones for different voltages.
Yeah,
That's
like-
correct.
No,
it's not. It's like 4.
It looks almost like English.
Yeah, exactly.
Yeah,
But
kinda.
they have a prawn setup where you can like insert it.
Right. Yeah. You. By the way, you can't go to Europe and take your hair dryer and plug it in because they won't fit into the. They have different prongs. Okay. Ours are the flat ones. I think those
wires.
are. Yeah. So you get a couple alligator clips and hook it on and shove it into the wall. It'll burn up. Okay. Now,
That's what they have to do.
the opposite of Kirchhoff's rule is that I've already said that if you supply more energy, then what will happen is it'll readjust to use all that energy up if it can, or it'll burn out. The opposite is if you supply less energy, the thing can't consume more than what you supply. So the device will consume less energy. It'll reach a new equilibrium, okay? So essentially, this just sets the equilibrium of the circuit. Okay, if you supply more volts, it'll consume more volts. If you supply less volts, it'll consume less volts. And that's what a dimmer switch does on your wall, essentially. If you have a dimmer switch for the lights, as you turn that, what it's doing is allowing less electricity, less voltage to go to your bulbs, so they'll dim out, or more, so they'll brighten up. Okay? And that's also what happens like when your air conditioner or hair dryer kicks in at home. Your lights sometimes will dim out and they'll come to the new equilibrium because of this. Alright, this one's easier to understand. The current rule. The current rule is real simple. Okay, right here, current. Current is a physical thing. So you get current going this way. Well, how does the current here compare to the current here? Why?
Resistance.
Yeah, because it's got nowhere else to go, right? It's got to go through this wire to here. But then when it gets to here, it's got a choice, right? It can go this way or this way. So the current rule simply says the current that comes in to a junction must equal the amount of current that goes out of the junction. Okay, so it'll be split up. So if this is current 1, and that's current 2 and current 3, then current 1 must equal current 2 plus current 3. Okay? And that's it. Now let's apply those ideas to series and parallel. Okay? If I apply the current rule to this device right here, what does the current rule tell you about series? Yeah, the current has to be the same everywhere. Okay, if it's series, the current in that resistor and that resistor and that resistor is the same as the current that goes through the battery. It's all the same. Okay? Now, this is also important because an ammeter measures current. It measures the current that goes through it. An ammeter measures the current that goes through it. So, everybody, if I put an ammeter here and I put an ammeter here,
That's the same.
it's going to read the same thing. Right?
Yes.
Piece of cake. All right? Okay, now let's apply voltage rule to this. If I apply the voltage rule to this, ooh, this is a little more complicated. If I apply the voltage rule and I start right here and I work my way around, what does it say? It says that the first thing I reach is this. The EMF of the battery right here must equal how much voltage I have across here, the voltage drop I have here, and the voltage consumed here, and the voltage consumed here, right? So technically the way you write this is I have positive voltage put in, and then I have delta voltage for resistor 1, and I have a delta voltage for resistor 2, and I have a delta voltage for resistor 3, and all that adds up to 0, right? We're going to rewrite that. We're going to say that the voltage total supplied to the circuit will equal the delta V for resistor 1 plus the delta V for resistor 2 plus the delta V for resistor 3, right? Is everybody okay with that? All right, now watch this. This is kind of fancy. But what does V equal? IR. That means that the IR total for the circuit equals the IR for resistor 1 plus the IR for resistor 2 plus the IR for resistor 3. Everybody okay with that? Now watch this. This is really cool. Well, what's I?
The same everywhere.
The same. So that means the total resistance in series equals R1 plus R2 plus R3 plus however many you got. So we just derived the equation for resistance in series. Anytime you have resistors in series, you can just add them all up. And they'll equal the same thing. You can replace those three with just one of whatever the sum of all those are. Now, let's talk about a voltmeter real quick. A voltmeter measures the difference in volts between its two sides. So one side plus, one side minus. Okay? So tell me, everybody, if I put a voltmeter right there, what will it read?
0.
It'll read orange minus orange. And even in math class, orange minus orange equals 0. Okay, so can we hook up a voltmeter in series? No. So how do we hook up a voltmeter? Yeah, so if I want to find the voltage difference, this voltage difference, I have to hook it up like this, between two separate spots, in parallel. So voltmeters go in parallel, ammeters have to go in series. Okay? All right, so if I want to measure the current that goes through this resistor, then where do I put the ammeter?
What?
If I want to measure the current that goes through this resistor right here, where do I put the ammeter?
Above, below it.
Can I put it right here?
Yeah.
Can I put it right here?
Yeah.
Yeah. Does it matter?
No.
No. Because the current here and here and here are all the same, right? Because there's no other place for it to go but through that line and that resistor, right?
Yeah.
Okay, now let's apply our rules of current rule and voltage rule to parallel. Okay, in parallel, what does our voltage rule tell us?
The volts, sum of the voltage or the potential difference around the loops should be 0.
Yeah, the sum of the voltages around the loops should add up to be 0. But look what I've got for my loops. I've got this loop. So that means that that equals that. And that means I got this loop, which means that red to purple equals red to purple. And I got this loop, which means I got red to purple equals red to purple. Or I could go around this loop, which means that difference and that difference have to be the same, right? So what does the voltage rule tell us?
That parallel resistors have the same voltage.
Yeah, every component that's in parallel must have the exact same voltage.
Which is why you can look up the voltage.
All right.
Parallel.
So parallel actually turns out to be simpler because of that. And they don't seem simpler at first, but they are. So the delta voltage for each component is the same. Now let's apply the current rule. All right, our current rule. We have current that goes through here. I'll call that the total current, because that's the mother of all currents.
Who's the father?
It's a single parent family.
Oh, we don't have
Dad didn't hang around. All right, right here, I'm going to call that current 1, current 2, and current 3 for my resistor 1, 2, and 3. Okay, so what does the current rule tell me about these four? How are they related?
1, 2, and 3 are the equal I.
Current total equals current 1 plus current 2 plus current 3. But wait! Didn't I tell you that this is a really cool relationship? And so that means that delta V over delta R total equals delta V over delta R for resistor 1 plus delta V over delta R for resistor 2 plus delta V over delta R for resistor 3.
And all the delta V's cancel.
Why do all the delta V's cancel?
All the same.
Because they're all the same. Now, when I cancel all of these, does that mean that R total equals R1 plus R2 plus R3? Okay, that would be a bad math thing, right? I leave a 1 behind, so 1 over R in parallel, parallel, how do you spell it? Equals 1 over R1 plus 1 over R2 plus 1 over R3 plus however many you got. So there's how you add up resistors in parallel. Now that is really weird how they add up, because think about it. If I have two 10 ohm resistors and I add them up in parallel,
Smaller.
I get a total resistance that's smaller.
But it's really not weird because there's less competition to go through each thing.
Yeah, it seems weird at first, because if I had two 10 ohm resistors together, you would think it would add up to be 20. But it only adds up to be 20 if they're hooked up like this. If you put two 10 ohm resistors in here, in parallel, just two of them, you end up with only 5 ohm resistance. 1 over 10 plus 1 over 10 equals 2 over 10, or 1 over 5,
So it's 5.
the inverse.
and then you invert it, and so you get 5 ohms of resistance. Now it seems odd at first, but what you're doing is every time you add a new pathway, you're allowing more current to go through, because you're opening up a new pathway for charge to flow. Okay? It's like we have two doorways back here. If we have only one doorway, it can only handle so much current students going through. If I open up another doorway, even if the doorway is a small doorway with lots of resistance, I've allowed more passageways for you to flow through, right? Yes.
Less pushing, shoving overall.
By the way, if one of these doors is like those doors, like the lab door, where the top opens and the bottom opens, and then we only open up the bottom, okay, then the door that's only open on the bottom would have more resistance. So which of the two doors will get more flow of students? The open one. But will some people take that door?
Yeah.
Sure, but not as many, right? The same thing happens in parallel circuits. In parallel circuits, if you have several pathways and one has a lot of resistance, well then not a lot of charge goes through that one. But some still does. Okay? Now in series, if I have a big resistor here and a small resistor here, you're stuck. You got to go through that one to get to that one, right?
And you have to go through that too.
And then you got to go, yeah. So you're stuck. You got to go through every one. But when they're in parallel, You can pick and choose, and the current does. The current won't be the same. All right. So, let's solve a couple of problems. A couple of easy ones first, and then we'll do a combo. All right. There's your circuit. I want you to tell me, what will the 2 ammeters read? And what will the 2 voltmeters read? Okay, somebody said that the 2 ammeters are the same. Is that correct?
Yes.
Okay, the 2 ammeters will be the same. So, excellent.
Yes.
We just don't know what that is yet, right?
1 amp. 1 amp. We do 1 amp.
Okay, now wait a minute. We had people saying that's 1 amp.
Yeah.
Okay, walk me through it. How'd you do it?
B equals my, combine the total resistance if they're in series.
Okay, if I was to color this circuit, this would be red.
Because it will split up.
No, we're
This would be
assuming
like
that the
orange or
voltmeter-
something.
Amps will go through the volt.
This would
those
be
are-
maybe
and
green.
we don't split.
Yeah, but we're gonna assume it doesn't do that.
And this would be violet, right?
I'm pretty sure we assume we don't do that.
Well, red.
Yeah, but we assume.
Now, the thing is that in order to find what the ammeter reads, the ammeter reads what? Delta V over delta R. Now, this is really important, everybody. This is the thing that makes circuits easy if you get this. Whenever you use Ohm's law, if you're trying to find the current through resistor number 1, you have to use the resistance of resistor number 1, and you have to use the voltage across resistor number 1. Or you have to use the total, and total. See what I'm saying? They always have to be matched up. So, the nice thing about series is that the current is the same everywhere, right? So you could either find the current for this one, or the current for this one, or the current for this one. So if I want to find the current here, that's the velocity, the voltage through the 6 ohm resistor, the resistance of the 6 ohm resistor, and I'll find the current through the 6 ohm resistor, right?
Yeah.
Do I know the resistance of the 6 ohm resistor?
Yeah.
6 ohms.
Good.
Do I know the voltage across the 6 ohm resistor? What's the only voltage I know?
The total.
The total. Okay, so back up. I know the total voltage. Do I know the total resistance?
Yes.
What is it?
Some.
6 plus 4 plus 2. So 12 volts over 12 ohms gives me my 1 amp. Does that make sense?
Yeah.
Okay. So now that I know the current, can I find the voltage here? Okay, the voltage here equals IR. The current through this resistor is 1 amp. The resistance of this resistor is 2 ohms. So I get 2 volts. Okay, now wait a minute, right here. I'm connecting up red to green. So V equals IR. The voltage across the 6 plus 4. I need the current through the 6 plus 4 and the resistance of the 6 plus 4.
Current's the same. 1.
Ah, the current is 1 amp, right?
10 ohms.
Oops, 1 amp. And the resistance of 6 and 4 is 10 ohms, so I get 10 volts.
Mr. Bruin.
Got
When
it?
we hook up a voltmeter, we assume no current flows through it.
Okay, good point.
Yeah.
Everybody, whenever we hook up a voltmeter, we assume our voltmeter has no current going through it. Now that means that our voltmeter, in theory, has how much resistance?
Infinite.
A whole lot, right? We assume
Approaching
that
infinity.
none of the current gets bled off here. So that means a voltmeter has infinite
Amount of
resistance. Not really, but yes.
Infinite.
And so,
If
wait a
you
minute.
actually did this lab though, you couldn't do that, right?
If we actually did this lab, we would assume that the
would?
voltage, our voltmeter is good enough.
But would the data give us that?
The data will be pretty close.
So our amp, like those 2 amp things would
Yeah,
still
like
equal, even
like
though
if
there's
you
some
if
that
you
would
measure
go
this
off?
voltage here and this voltage here,
No,
it
the
probably won't
ammeters.
end up being exactly.
No, I was saying the ammeters. Would they show up as even?
Ah, now ammeters. In order for an ammeter not to mess up the circuit, what's its resistance have to be like?
None.
Has to be none. So what we find out is if I put an ammeter in this circuit, it wouldn't read exactly 1. It would probably read a little low.
No, what I'm
Lower.
saying though is the fact that the voltage meter's there, the current's going to split. So then, therefore, that ammeter should show less because the current split.
Now, that in the real world, yes. In our imaginary world of physics, right now, we'll assume that to be small enough not to worry about.